Hello class 12. Starting with this video, we are going to start a portion of physics which is called optics. And like I've already told you, there are two branches of optics. One is called physical optics or wave optics, and the one that we are dealing with right now, or we have started with, is geometrical optics, or also called ray optics, wherein of course we are going to talk about reflection, refraction through whatever kind of a surface. Okay, we are going to talk about lenses, microscopes, telescopes. All right. So the first thing that we are going to start with in ray optics is a very familiar topic, okay, which is refraction through a prism. Now you've dealt with this particular topic in class 10 itself. Okay, so what we have is, as you can see, we have a prism ABC. This A, or rather this angle, is also called the angle of the prism, simply depicted by an A. And what we have is, we have a ray of light PQ actually moving in this direction, which is PQDE, or you can simply say PQE. The ray of light is traveling in this direction. And when I say ray of light, what I mean is, I mean to say this is a monochromatic ray of light. Now, it's not that only monochromatic ray of light will suffer refraction through a prism. Okay, also a polychromatic ray of light like white light also suffers refraction. But here specifically I am talking about monochromatic ray of light. Now, if you ask me what is monochromatic, monochromatic ray of light means a ray of light having a single frequency, one frequency of light. So to say, it has a definite color of its own. Alright, mono of course means one, as you already know. So we have PQ, a monochromatic incident ray, being incident on the prism, because of which it undergoes refraction. Now, since the ray of light is coming from a radar and traveling to a denser medium, it bends towards the normal, this being the normal. Now what happens, this ray of light again suffers refraction on the second face of the prism. Now QR, so to say, is the incident ray now. Now, since the ray of light is coming from the denser medium and traveling to the radar medium, it moves away from the normal. So RS is the refracted ray of light in when refraction takes place on the second phase, so to say, or rather we prefer to call it the emergent ray. RS is the emergent ray. So I is the angle of incidence, R1 is the angle of refraction, R2 is the angle of incidence for refraction taking place on the second face of the prism, and E is again the angle of refraction, or rather we prefer to call it angle of emergence. Okay, so this is about refraction, remember, and these are the different relations that we come across when we talk about refraction through a prism. Now these relations can actually be derived, and it's not a very elaborate derivation. These are very simple derivations. So I suggest you to give a look at those simple derivations. Okay. So what we get to see is R1 plus R2 is equal to the angle of the prism. So this R1 plus R2 is equal to the angle of the prism. Likewise, the second relation tells us the angle of incidence plus the angle of emergence minus R1 plus R2, that is this thing on the left hand side, is equal to the angle of deviation. Now what is this angle of deviation, denoted by a Greek letter delta, of course? It is simply the angle between the original direction of the ray of light and the eventual direction of the ray of light itself. Or so to say, it is the angle between the direction of the incident ray and the emergent ray. So the angle between the incident ray and the emergent ray is what is called the angle of deviation, which is this angle over here, and is denoted by delta, like I've already told you. So I plus E minus R1 plus R2 is equal to delta. Now since R1 plus R2 is equal to A, this equation or relation 2 can be rewritten as I plus E minus A is equal to delta. Like I already told, you can give a look at the simple derivation. It's not very difficult, it's very easy. Okay. Now, before we jump into relation number 4, let us pay attention to this graph. This, of course, is a graph which you've already seen. It is the graph of the angle of deviation versus the angle of incidence. Now, this lowermost point, at this lowermost point, the graph, as you can see, is U-shaped. Alright, so at this lowermost point, this lowermost point, so to say, gives us the value of delta m, or delta m is, so to say, the angle of minimum deviation. Alright, so for a given monochromatic light and for a given material of the prism, you get the angle of minimum deviation denoted by a delta m, of course. Okay, say this is the angle of minimum deviation. So for the angle of minimum deviation only from the graph, we see that there is one value of the angle of incidence, which is this. Whereas for every other value of the angle of deviation, say this value, for every other value of the angle of deviation, what we see is we get two values of the angle of incidence, one over here and the other over here. You can check at any other point. Okay, for other values, for any other value of the angle of deviation, we get two values of the angle of incidence, except for the case of minimum deviation when we get only one value of angle of incidence. So what do we understand? For any other case, when we get two values of the angle of incidence, one value of course is the angle of incidence I, the other value is giving us what? The other value is giving us the value of the angle of emergence, because when we make the ray of light incident from this side, say this is the incident ray now and the angle of incidence is equal to E, then what happens is the ray of light will finally emerge out in this direction at an angle of emergence equal to I. This we get from something called principle of reversibility of light. So if I is the angle of incidence, E will be the angle of emergence. Likewise, if E is the angle of incidence, then I will be the angle of emergence for the same value of the angle of deviation. Okay, so this is what two values of angle of incidence tells us. Except, like I already mentioned, for the case of minimum deviation, when there is only one value of the angle of incidence, meaning for the value of the angle of minimum deviation, that is for the case rather of minimum deviation for delta m, we get to see that the angle of incidence is equal to the angle of emergence. This is what we understand from the graph. Or for this case, what we have is we also get to see for this case, therefore, R1 is equal to R2. Alright, so since I is equal to E and R1 is equal to R2, thereby we have this. For the case of minimum deviation, the refracted ray QR, will be parallel to the base of the prism. This is specifically only for the case of minimum deviation, remember that. Okay, so for the case of minimum deviation from relation 3, we get relation 4. Because delta is delta m for minimum deviation. And since E is equal to I, this becomes 2I minus A. So delta m is 2I minus A. And of course, the following relations are also for the case of minimum deviation. This number 5 is simply Snell's law. It is simply Snell's law. Okay, the refractive index of the material of the prism, for refraction taking place on the first phase, the material of the prism is the second medium, so to say. So refractive index of the second medium is equal to sine of angle of incidence divided by sine of angle of refraction. Because for case of minimum deviation, from here we can see that angle of incidence I is equal to delta m plus A divided by 2. So delta m plus A divided by 2 is the angle of incidence. Likewise, since R1 is equal to R2 for delta m, so from here 2R is equal to A, or so to say R is A by 2. So therefore sine of angle of refraction. Understood? Now, this case 6 of course is for the case of minimum deviation, but in addition to that, number 6 is specifically for the case of thin prism. Thin prism meaning when the angle of the prism A is very small, the value of the angle of the prism is very small, then we have delta m is equal to eta minus 1 into A. You can check the derivation for this also. Okay, it's very 2-3 lines. Okay, you can give it a look. So for thin prism specifically, mind you, delta m is equal to eta minus 1 into A. So whatever I've spoken so far I've spoken about things that you already know or that you've dealt with in class 10. Okay, so let us now give a look at something, more of the standard of class 12. All right. So let us now talk about something called angular dispersion. Angular dispersion is denoted by a theta. But before we jump into angular dispersion, let us talk about something called dispersion of light. What is the phenomenon of dispersion of light? The splitting up of white light into its 7 constituent colors when it is passed through a prism is what is called the dispersion of light, which I have tried to depict in this picture over here. So we have white light coming. The moment it enters the prism, what happens is this white light splits into 7 constituent colors, and this is what we get, as the emergent rays. The 7 constituent colors, 7 different colors. So phenomenon of splitting of light is called dispersion of light, and this is called the 7 constituent colors that we get coming out of the prism is what is called the visible spectrum of light. Okay, so we have violet, the bottommost light here at the very bottom, VIBGYOR, this is what we get. Now, why does this white light split? The very fact it splits is because different colors of light travels with different speed in any medium apart from air or vacuum. So to say, the refractive index of a given medium is different for different colors of light. So the refractive index of the material of the prism is like eta R for the red color of light, it is eta V for the violet color of light, because all different colors, they have, the value of the refractive index of the material of the prism is different for 7 different colors of light, all different colors of light, so to say. Therefore, all these different colors, they travel with different speeds in this medium, and thereby they split. Okay? So, what is therefore angular dispersion? Angular dispersion, as I've written over here, is the angle between the emergent rays of any 2 colors. Okay, or so to say, the angle between the emergent rays of any 2 colors is what is called angular dispersion between those colors of light. Remember that. So what we basically take over here is, we take the 2 extremes. This is V, this is R. Okay, red light and this is violet light. So the angle between the emergent red light and the emergent violet light, depicted by this angle over here, theta, is the angular dispersion between the red and the violet colors of light. For different pairs of emergent light, of course, the angular dispersion obviously is going to be different. Okay, so we've chosen red and violet light, the 2 extremes here. So the angle between the red emergent light and the violet emergent light is what is called the angular dispersion between the red and violet emergent rays of light. Now you can see from this picture here, if theta is the angular dispersion between red and violet light, then this white light, or so to say violet and red combined, was initially moving in this direction as depicted by the dashed lines, broken lines over here. Okay, but eventually red is emerging in this direction and violet in this direction. So to say, delta R is the angle of deviation of red light and delta V is the angle of deviation for the violet light. Now, to be more specific, what we consider is, we consider the case of thin prisms, considering the case of thin prisms, such that the value of the angle of prism is very small. So, considering thin prisms, delta R is the angle of minimum deviation for red light and delta V is the angle of minimum deviation for violet light. So, if that's the case, then angular dispersion, as you can see from, that is the value of this angle, as you can see from this picture, is delta V minus delta R. So, angular dispersion theta for between red and violet light is equal to delta V minus delta R. Okay, so this is how angular dispersion is defined, and here is its definition. You can pause the video and copy the things here because I'm going to erase this. That is the definition. Now see, let me start from here itself. If it's a case of thin prism, then for violet light, what we can write is, we can write delta V is equal to eta V minus 1 into the angle of the prism, where eta V is what? It is the refractive index of the material of the prism for violet light, and likewise for red light we can write delta R is equal to eta R minus 1 into A, where eta R of course is the refractive index of the material of the prism for red light. Okay, so from this relation and this relation, so to say, substituting the value of delta V and delta R here, we get theta is equal to eta V minus 1, alright, minus of eta R minus 1 inside the bracket, and of course what I've done is I've taken A common outside, or what do we get from here? Theta is equal to minus 1, this becomes plus 1, so 1, 1, they cancel each other out. We have eta V minus eta R into the angle of the prism. So this is the final expression or final result that we get for angular dispersion. This is the final expression for angular dispersion. The angular dispersion is equal to the refractive index for violet light minus refractive index for red light into the angle of the prism. Okay, so this equation depicts the angular dispersion between red and violet light. Remember that. So this is basically about angular dispersion. What we are going to look at next is something called dispersive power. For that, let me erase all these stuffs that I've written here. You can pause the video. Something called dispersive power. Dispersive power of the prism, of course. Okay, dispersive power of what? Dispersive power of the prism. It is denoted by an omega mod W. Now what is dispersive power? Dispersive power is the angular dispersion between red and violet light, that is the two extreme light. Okay, so it is the angular dispersion between red and violet light, which of course is given by this divided by the deviation for the mean ray of light. Now considering thin prism, the mean ray of light in VIBGYOR is supposed to be green, but we take the mean ray of light to be yellow. Okay, so the deviation, so your yellow is somewhere over here. Okay, the yellow is not here. The yellow is somewhere over here. Here. Alright, so the ratio of the angular dispersion between red and violet light to the deviation suffered by your yellow light. So this was the direction of white light, so this deviation, delta Y, so to say. The deviation suffered by yellow light is what is called the dispersive power of the prism. It has to be angular dispersion between the two extreme lights, remember, that is red and violet. So this is how you can define. The dispersive power of the prism is defined as the ratio of the angular dispersion between red and violet light to the deviation, or so to say the minimum deviation suffered by the mean ray or the yellow color of light. And delta y is minimum deviation, mind you, because we are considering the case of thin prism. So this can be written as eta v minus eta r into A divided by, for yellow light, what we can write is eta y minus 1 into A for delta y, where eta y is what? The refractive index of the material of the prism for yellow light. Okay, so A and A, they divide each other out, and finally therefore we get the dispersive power is eta v minus eta r divided by eta y minus 1. Okay, so this is the expression for something called the dispersive power of the prism. This is the expression for the angular dispersion. Now, you might ask, although green is the mean light in VIBGYOR, but why do we take yellow to be the mean? Okay, it is because of the fact that our eyes, okay, it's most sensitive to yellow color of light rather than green. Okay, in fact, of all these different colors, you know, like I already told, it's most sensitive to yellow color of light. Therefore, we take yellow to be the mean ray of light here. So this is the expression for dispersive power, angular dispersion. Thank you.